Hey everybody, this is Larry. This is me doing day 12 of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about today's problem. Number 23, merge case sorted list. So I'm in New York, it's Saturday today, even though I think today, the problem is Sunday, but wherever you are, I'm a couple of days late. So, uh, uh, um, a few celebrations around the city for Holly. So definitely, like I said, I know I'm a couple of days late, but to whom celebrates the holiday, holiday. Huh. Anyways, if you celebrate, hope you enjoy. Hope you had a colorful weekend or week or however you celebrate it. You know me. I'm a little bit silly, so I'd like to get into it though. This time I don't know. I didn't really set something up. I don't know. This year's just been a bit weird for me in general. Maybe I'll talk about that in another time. Anyway, today's problem is number 23, merge Kate sorted list. So this one, it's I don't know when the last time I did this video because didn't feel that long ago. But in any case, so there are a couple of ways you can think about this, right? I mean, I often use I often used these linked lists as a metaphor for different things. I mean, and of course, it still works with linked lists, but I think, like, if you do enough computer science or whatever, and sometimes you do wonder about the real world application of this, and this is actually one of those things that does come into play where this could be an idea about if you take the scale to a huge level, could be like things in like map reduce or something like this, right? Merge is a important part of the steps, and I think the canonical way of accepting is also, or thinking about it, is also like, let's say you have you have K hard drives. Each of them has sorted list of numbers. How do you kind of do that while not having all the having the capacity to put everything in memory, right? Because if you have everything in memory, do an n log n sort, you're done. So anyway, that's kind of like the idea, and there's a lot of history about it, and it is interesting. So definitely, if you definitely play around with ideas, but as it is, this problem is going to just be a linked list. So let's get started. I mean, the way that, so there are two parts of this, right? One, as it is for most of these problems, as I always say, there's the algorithms part, and then there's the implementation part, right? The algorithms part is kind of this idea of using let's start with k is equal to 2, right? If k is equal to 2, then you just have a merge sort, or the merge step of the merge sort, right? And you could kind of do it that way as well if you really want to. I don't know, and you can maybe do the math on the complexity of that, right? But the other way that you can do it is by just using a heap, right? Basically, you're just getting the smallest, or the linked list with the smallest head every time, and then just keep going until you're done, right? So let's let's do that. Yeah, I mean, there's some stuff that is kind of Python-y, like a little bit weird, possibly, because comparison between list nodes, I don't know how they do it, but we can get started on it. So heap is equal to so then now for list, maybe that's not a good variable name, but for L in list, that's still not a great variable name, but my Q key is a little sticky. I think I was eating near it earlier. Anyway, so now we want L, but we also actually want to index first by because a list. I just wanted to check whether it could be none. So if it's none, then we don't care. So if L is none, then we continue, right? And then maybe L dot value L, right? Because that's the first node, assuming that L is not none. I think this is syntaxically correct. Let's take a look. Yeah, that's what I was worried about. How do I want to do it? I thought that there may be, but I mean, we could implement something, but um, hmm. I mean, this is the implementation part that I was thinking about. That and there are a couple of ways you could do it. You could just do it by a calendar or something like this, right? So then now you can just say this is an array, and then now you have index, right? And then now you have index, and then out. The reason why adding an index, even though it doesn't do anything, or I mean, I guess it does something, but the reason why adding index gets rid of the error message is because now, because index is unique, right? It's unique on all the list. So that means that so what happens in a heap or comparison in general of tuples is that it looks at the first element between two elements or two first element of one tuple and then the first element of this one the other tuple, do a comparison, and then if it's not equal, then it just does a comparison, but if it's equal, then it goes to the next element, right? And before, without this index, it was doing a comparison on the second index, which is the L, and now it's doing. And L is a list node, the head of the node. So now it's doing comparison between two nodes, and it doesn't know how to do it, right? But if you add an index, the thing is that now it will never go to do a comparison on the third index, on the third element, say, of the tuple, because index is unique. So that's basically the reason why. And for the purpose of this problem, I think it doesn't really matter anyway, with respect to or what I mean by that is that if you have two ones, it doesn't matter which one gets the next item, I think. So yeah. So then now we do while length of heap is greater than 0. So value we don't care about, index we also don't care about, and then the node is equal to heap q dot heap pop of heap. We also need let's say new head is equal to list node of -1. And then current is equal to new head, right? And then here now we set current.next is equal to list node of node.value. I know that in theory we could take this node and then change the list pointers, but I don't want to do that hassle. And also, like, yeah. But this is good. And then now current is equal to current.next. And then this part is good, but then now we have to put it back, push heap, and then now we want so basically if node.next is not none, then we put node.next.value, index, and then node, right? So actually I guess we do one index here just for that purpose again, and I think that should be good. And then now we return new head.next. Yeah. Unless I have an infinite loop somehow. Oh, why does this infinite loop? We pop. Oh. Silly. Whoops. Obviously, you go to the next item. Okay. I guess I was going to do some empty cases like this one. Let's also do another one anyway. Because I don't know, it's very easy to make mistakes here, so. Yeah, I mean, apparently I solved this 5 times. Well, this is the 5th time, so I'm glad that this is pretty good. What is the complexity here, right? Well, each D heap is going to take, or heap pop is going to take log of n. I don't want to use n because n is usually the size of the input, and the size of the input is the summation of all the number of nodes, right? Generally speaking. So let's say L is the number of items in this list, then there is going to be log L. Well, this one is just log L once in the beginning, but yeah, it's going to be log L for each item. So it's going to be O of n times log L, where n is actually the number of total elements in the list, right? and log L is just the number of lists. So yeah, so this is the time, and this is O of n space, because you need it for the heap. Yeah, and the reason is because this heap, it will run as many times. Sorry, let me try again. This heap will get O of n items, right? And then each of these will take log L to pop and log L to push. So that's n log L. That's like a tongue twister, isn't it? Anyway, cool. Let me know what you think. Let me know if you have any questions. That's all I have for today, because there'll be a contest later. So I'm just gonna, I don't know, take a nap or something. I don't know. I'm old. Old man Larry is tired. Anyway, so yeah, so stay good, stay healthy, take good mental health. I'll see y'all later and take care. Bye bye.